Welcome to the Math 3 lesson summary video for the task Inverse Universe. The purpose of this task is to become fluent in identifying inverse functions by analyzing various representations of functions and their inverses. For this task, you'll need cards provided by your teacher. If you don't have those cards yet, you'll need to first get them before you watch this video. You can also print them online. First, we want to select a card from your set. You'll either have the A or B set and show it to your partner. Then you're going to work together through your partner's cards to find the match that represents the inverse of your card. Record that match and the reason that you selected it, and then repeat the process until all of the cards have been paired up. So all in all, we're looking for 10 matches from the A card set with the B card set. So each A matches with a B. Before we dive in, we want to remember the three key relationships among inverse functions. Number one, from the tables, every xy point gets reversed to become yx in an inverse function. So to tell if two functions are inverses from their tables, we're looking for input-output pairs being switched. On a graph, that would look like the two graphs being a reflection over the line y equals x. And from the function rules, we can tell that two functions are inverses if they are opposite operations in the reverse order. Let's say I start with card A4. Graphically speaking, I would be looking for this blue graph, which is a reflection of card A4 over the line y equals x. However, when I consider all of the B options, there's no graph that matches the blue graph that I created. B5, B7, B9, they don't look like the blue graph. So we have to think of it in a different way. Let's make a table of sorts for A4. We have the point -3, -2, 1, 0, 6, 1, and 13, 2, as well as the point -2, -1 that I didn't label here. Looking at the B options now, is there any table that has these points reversed, where the inputs become the outputs and the outputs become the inputs? We can see B8 does that, in fact. -3, -2 became -2, -3. 1, 0 became 0, 1. 6, 1 became 1, 6. 13, 2 became 2, 13. So A4 and B8 are inverses because the table representations of each card clearly show that the input-output pairs have been switched. Consider now card A3. I have a verbal description given. Each input value x is squared and then 3 is added to the result. The domain of the function is 0 to infinity. I can write an algebraic representation of that, and I can see it's a quadratic function with a restricted domain that's only going to be x values bigger than 0 or equal to 0. From this function in algebraic form, I can write the inverse function. The opposite of squaring and then adding 3 is subtracting 3 and then square rooting. And instead of restricting the domain of an original function becomes the range of the inverse, so we would restrict the range of the inverse function. So I'm either looking for a function rule that matches this exactly, or a graph that's a square root function for y values only bigger than 0. So we can begin to use a process of elimination on our B cards. B8 can't be the match because we've already used that in another match pair that we're confident with. B1 is not a match because that's the incorrect function rule. Doesn't match what we just stated. Same reason to eliminate B2. We know the inverse function is a square root function, so B3 is eliminated because that is a linear function that's being described. B4 can be eliminated because it has negative y values that we know can't happen based on our restricted range for the inverse function that we just created. B5 can't be a match for the same reason due to its negative y values on the graph. That leaves B6, B7, B9, and B10 as possibilities. And as we look further at B6, we can see that is the inverse function. To make it even more clear, it's helpful to look at a graphical and table representation of function A3. So we have the quadratic function x squared plus 3 on the restricted domain, 0, 3, 1, 4, 2, 7, and 3, 12. And we can clearly see how these points in the table for B6 are the reverse of those points. 0, 3 became 3, 0, 1, 4 became 4, 1, 2, 7 became 7, 2, 3, 12 became 12, 3, and the pattern would continue if we compared both function rules. The function rule that we originally generated for the inverse, you can see, does indeed fit for the table in B6. Notice that we said f inverse of x would be the square root of x minus 3 for y values that are all greater than or equal to 0. All of the y values in this table are greater than or equal to 0. And for example, for one of the points we haven't tried, if I substitute 19 into this function, 19 minus 3 is 16, and the square root of 16 is indeed 4. So you can see that this table does match the rule we originally came up with. So the key idea behind this task is it's important to be able to convert between the different representations of functions, tables, graphs, rules, verbal descriptions in order to be able to determine these matches. So if you can't find a match from the first representation you try, well then try another representation. And I generally find tables to be the most effective. I like to make tables for almost everything in this task. Thank you for watching this video. You'll have several other matches to determine on your own now that you've got the hang of it. And make sure you're writing down your reasons for each match. If you need help with the Ready, Set, Go problems for this task, be sure to check out the Canvas site for your class and the Ready, Set, Go support videos located there.